Welcome everybody to the 8th lecture of Informatik 1. Today we will cover the history of computers and also dive into number systems. Before we start with this lecture, we need to first define what is computer science. And computer science is in Deutsch Informatik. So computer science is the science of automatic information processing. And in German, the word Informatik consists of the word information plus automatic. And computer science is more than just computer science. It also covers the automatic information processing in nature, technology, and also in society. And as Edgar Dijkstra once said, computer science is more than just computer science, same as astronomy is not just about telescopes. So yeah, it covers a whole lot more. The history of computer science covers 3 subdomains. The first one is mathematics. So it all started off with plain mathematics. And then after the wheel got invented, scientists tried to implement some of this mathematics using mechanical devices. And then after the electronic revolution, so to say, the mechanical parts inside computers, for example, got replaced with electronic parts. Or one could also say from the abacus to the quantum computer. Considering that computer science is more than just computers, let's take a look at what we have already learned in this course. First, we started with an introduction to programming, where we covered the different programming tools and learned the basics of the Python programming language. Then we moved on to one specific subset of computer science, namely data science. In these lectures, we learned the so-called data analysis pipeline, and more specifically, we learned how we can extract data from various data sources like the file system, how we can clean and filter the data, how we can perform basic calculations on the data, like calculating means or the sum. And finally, we learned how we can visualize the processed data in order to gain a better understanding of the underlying information in the data. The last step in the data pipeline is the action step, where one can apply machine learning models on the data in order to make predictions or classifications. We won't cover this last step in the course, however, I will give you a brief glimpse into that topic during the last lecture. And if you want to learn more about this last step, you should definitely visit the follow-up course, namely Informatik 2, in the next semester. In this lecture, we take one step back and take a look into the history of computers, as well as the mathematical basics, in particular number systems. And in the next lecture, we will briefly discuss some basics about the internet. Without the history of computer science and the mathematical basics, we wouldn't have been able to look at the basics of the Python programming language, which resulted from all these achievements. That said, let's take a look at the history of computers. If we would be in the lecture hall, then I would show you this YouTube video, which basically covers the complete history of computing in a very nice way. However, since we are not in the classroom and I can't show you the video, I will just put the link to this YouTube video inside the description of the YouTube video, of this YouTube video, which you're looking right now. And I will also put the link into the Teach Center. Alright, so assuming that all of you have watched the video, let's move on to number systems. So the first number system, which we all know, is the decimal system. And most number systems are based on counting with fingers. And therefore we also use the decimal system because we have 10 fingers. And yeah, therefore also most of them are also variants of the decimal system. So the base for the decimal system is 10, because we have 10 fingers, as already said. And the standard integer is in the decimal system. And we use the numbers 0 to 9 to represent the 10 states in the decimal systems. And yeah, in Python, we do not need a prefix if we want to define a number in the decimal system. So we can just write, for example, a number equals to, just a normal number in the decimal system, for example, 123. Or we can also, for example, just cast a string containing the string 99 into an integer, which is then a number in the decimal system. Then the next one very famous number system, which is widely used also in computer science, is the hexadecimal system. And as the name suggests, hexadecimal stands for 16. So it has the base 16. So we need to extend the decimal system, which has the base 10, consisting of 10 numbers, so to say. We need to extend that with 6 additional numbers. So in the decimal system, we had the numbers 0 to 9 to represent the 10 different states. And since we need 6 more states or 6 more numbers, we need to add characters. And in this case, we add the characters A to F. So we have 6 additional characters, namely A, B, C, D, E, and F. And in total, we have then, together with 0 to 9 and A to F, 16 numbers. All right. So it's basically the equivalent if we would have 16 fingers for counting. And the prefix in Python, if we want to define a hexadecimal number, is 0x. So we can define, for example, a hexadecimal number in Python by defining a variable name. For example, hex underscore number is equal to 0xf. And 0xf represents 15 in the decimal system. And we can just print it out. If we then print out the hex number, it will print out 15. So it will print out the value of the variable in the decimal system. So in the background, it converts the hex number into its decimal representation. And similarly, we can, for example, directly print out the value of 0xff. And if we print this out, it will print out 255. Here at the comment on the right side, you can see how we can get the decimal representation of this hexadecimal number. And later in the course, we will learn how we can come up with this calculation. Another very important number system is the binary system or the dual system, and it is especially very important in computer science since it is used in computer science. Basically computers work with the binary system. So maybe you have already heard somewhere that computers can only read 0 or 1s. And this is basically related to the binary system because all information is encoded in binary. Therefore we only have 2 states, namely current flows or current does not flow. So there's no signal if we think in terms of electronics. All right, so the binary system has the base 2, which means we only have 2 states, namely 0 and 1. Therefore, we only need 2 numbers, namely 0 and 1, to represent the state where the current flows, zu Deutsch, wo der Strom fließt, and 0 where no current flows, or zu Deutsch, wo kein Strom fließt. And we can represent binary numbers in Python using the 0b prefix. Similarly, we can define a binary number as follows. So we can just type our variable name where we want to store our binary number, and then 0b010, which represents the number 5 in the decimal system. And again, we can just print it out, and again it just prints out the decimal representation of this binary number. And yeah, we can also directly print out a binary number. And again, later in this course, we will learn how we can convert from one number system into another. So the binary system, as already said, is the foundation for a computer, since it is the reduction to two states. As already said, 0 means no current or voltage, so the switch is turned off. Zu Deutsch, kein Strom fließt, der Schalter ist ausgeschaltet. And 1 means the current or voltage is basically flown, or the switch is on. Yeah. So here you can see a binary number, namely 0010111. So it's a 8-digit binary number, or in other words, a binary number consisting of 8 digits or of 8 positions. And you can see the position on the right hand side is the 0th position, and the position on the left hand side is the 7th position. And then we can calculate the decimal representation of this binary number by calculating the sum of 2 to the power of the position. So if we look at the right hand side, we have 2 to the power of 0. And if we look at the left hand side, we have 2 to the power of 7. So we have just the base, which is 2, to the power of the position. And then we just build the sum of this. And yeah, since we only need to consider the terms where the binary number is 1, we just need to calculate these numbers, which is 2 to the power of 5, which is 32, and then 2 to the power of 3, which is 8, and 2 to the power of 2, which is 4, and 2 to the power of 1, which is 2, and 2 to the power of 0, which is 1. And then we can build the sum of this, which is equal to 47. And therefore, the above binary number represents the decimal number 47. So one single position is called a bit. So if one single position of a binary number is called a bit, or also binary digit. And the rightmost position is also called the least significant bit, or LSB. And the leftmost position is called the most significant bit, or in short, the MSB. So this conversion also works in the decimal system. So for example, if we have the decimal number 7413, we can just again write down the position. So again, the rightmost position, namely the 3, which has the least value, namely 3, has the position 0. And for example, at position 3, we have the 7, which is at a higher position because it has a higher value, namely 7,000. Yeah, and on the left hand side, we have the position 7. And in this case, yeah, our number is not big enough to have a value there. So we only have the number 7,413. So then, in order to come up with the decimal representation of this decimal number, we can just calculate the same sum. So again, we take the base, which is 10 to the power of the position, and then sum up all the numbers. So again, we just write down the decimal number times 10 to the power of 7 plus the decimal number times 10 to the power of 6, and so on. And again, we just need to consider those numbers where we have a value, or those positions where we have a value unequal or greater to 0. And in this case, the first value which we need to consider is at position 3 with the value 7. So yeah, we have 7 times 10 to the power of 3, which is equal to 7,000, plus 4 times 10 to the power of 2, which is 400, and then 1 times 10 to the power of 1, which is 10, and then finally 3 times 10 to the power of 0, which is 3. And then if we sum up these terms, we again end up with the decimal representation, which is equal to our initial decimal number. But as you can see, using this schema or this framework, we can basically encode our numbers. Since we are computer scientists, we should also have a more deeper understanding of the binary system, and therefore we also look at some basic arithmetic rules in the binary system. So here we have some basic rules for the addition in the binary system. So here you can see we have two binary numbers with the length of 2 bits. So here you see the first binary number with 2 bits, and here you can see the second binary number consisting of 2 bits. And yeah, as you can see, each bit is 0. So we have the binary numbers 0, and if we add them up, we get 0 as a result, as you can see at the bottom. And if we change the second binary number to 1, so the first bit of the second binary number is 1, and if we add the two numbers up, yeah, we have 0 plus 1 is 1, and that's it basically. And we can also, for example, change the numbers up. So for example, we have the first bit of the first binary number is now 1, and the first bit of the second binary number is 0, so we just switched up the numbers. And similarly, now we have 1 plus 0, and this is also obviously 1. Alright, so now let's look what happens if both binary numbers are 1. So the first bit of the first number is 1, and the first bit of the second binary number is 1. And if we add them up, we get 1 plus 1 is equal to 0, and we have 1 as a carryover. So we need to add 1 as a carryover. Zu Deutsch, this means ein Übertrag. Wir haben 1 als Übertrag. And then we need to add this 1 at the next position. Therefore, we get the result 1, 0. Alright? So this is then equal to the binary number 2. And the last variation what we could have is if we have the similar case, so two binary numbers with 1 at the same position, and if we additionally have a plus 1 carryover from the previous step, for example, we have 1 plus 1 plus 1 from the carryover. Therefore, we have as a result also 1, and similarly as previously, we also have the plus 1 as carryover. And therefore, the result is 1, 1. If we look at an example, it gets hopefully a little bit clearer. So here you can see we have again two binary numbers. Now we have 7 bits, which means the binary, we have 7 numbers basically. So the first number is equal to the decimal number 45, and the second number is equal to the decimal number 54. And we now start again at the rightmost position, and at the third row you see the carryover. There we will fill in the carryover, and the last row will contain the result. So let's start. We have 1 plus 0, which is 1. We have no carryover. Then we move on to the next column. There we have 0 plus 1 again, which is 1. We have no carryover. Then the next row we have 1 plus 1. We learned that 1 plus 1 without a carryover is 0. And we have 1 as a carryover now, so we put it there. And now we have 1 plus 0 plus 1, which is again 0. And we have a 1 as a carryover now. And now the next step we have 0 plus 1 plus 1, which is again 0. And we have now 1 as a carryover. And now you can see we have 1 plus 1 plus 1. Therefore, this is the last step which we learned. We have now 1 as a result and again 1 as a carryover. And now in the last step we have 0 plus 0 plus 1, which is equal to 1. And now we are finished. And if we convert this binary number into a decimal number again, we will get the result 99. So we now know how we can perform an addition. Now we look at the subtraction in binary, and the computer converts the subtraction into an addition using the 2's complement. And for example, if we want to calculate 1 minus 1, the computer converts this subtraction into an addition. And to do so, we need to negate the second number. So we perform 1 plus minus 1. So we need a way how we can represent negative numbers. And to do so, the MSB, the most significant bit, carries the information about the sign of the number. And we have some limits there. So when we think of that we have only n available bits to store our number, and the MSB, which is the leftmost bit, carries the information about the sign, then we only have a limited number of representable numbers. So the smallest representable number is then minus 2 to the power of n minus 1. And the largest representable number is 2 to the power of n minus 1 minus 1. Since 0 is counted as a positive number, we need to subtract 1 there. So now let's look into more detail into the 2's complement. The 2's complement is the most common method of representing signed integers. And signed means in German Vorzeichen-behaftet. So we can calculate the 2's complement as follows. So we just need to perform 3 simple steps. So if we have a given binary number where we want to compute the 2's complement, its negative representation, so to say, is we first need to invert all the bits of the number. So for example, if we have a 0, we invert it to 1, and if we have a 1, we invert it to 0. And after that, we just need to add 1 to this new number. And then finally, as the last step, if we have an overflow or a carryover, we just need to ignore it. And then we are done with the 2's complement. So for example, if we have the binary number 0 and want to calculate its 2's complement, we need to perform those 3 steps. So first we need to invert all the bits. And since each bit here is 0, so we have 3 0 bits, the resulting inverted number is all ones. So we have 3 ones there. And then we apply step 2. So we add 1. And then we need to calculate the result of this addition. So 1 plus 1 is 0 with 1 carryover. Then 1 plus 0 plus 1 carryover is again 0, again with 1 carryover. Then 1 plus 0 plus 1 carryover is again 0. And we have 1 carryover left. And this is the overflow as shown in step 3, and in this case we can just ignore it. And as you see, the 2's complement of the number 0 is 0 again, and this makes totally sense because the number 0 doesn't really have a negative representation, so 0 and minus 0 is basically the same. So this makes totally sense. So let's look at another example. So here we have the binary number 1. Now we again apply step 1, which is inverting all the bits. So if we start from left to right, for example, if we invert 0, we get 1. Then we invert the next 0, we have 1 again, and then we invert the 1, we get 0. So we just flip around each bit. Then we apply step 2, which is adding 1 to this new number, and then we calculate the result. So 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 0 is 1 again, and we are finished. And yeah, this is the 2's complement of 1. So this is the negative, or this is the representation of minus 1. And as you can see, the MSB, the most significant bit, which is the leftmost bit, is 1, which indicates that this is a negative number. And yeah, here you can see a table which shows the 2's complement of all 3-bit integers. So assuming that we have only 3 bits available, a 3-bit binary number, here you can see the table. So as we already said, or as we have already calculated in the previous step, if we look at the first row, we have the decimal value 0 and its binary representation, meaning 3 0 bits. And then on the right hand side, we have the 2's complement, which is again all zeros, as we have calculated the previous slide. And then at the second row, for example, we have the decimal value 1 and its binary representation 0 0 1. And we have also calculated in the previous slide its 2 complement, which is all 1, so 1 1 1, which is the representation for minus 1. All right, and then you can see the other values down there. So now we know how we can calculate the 2's complement, and we have already learned that the binary subtraction is equal to an addition with its 2's complement. So if we have 1 minus 1, the computer converts it into an addition, like 1 plus minus 1. And again, similarly as by calculating the 2's complement, overflows are ignored here. So if we have, for example, the decimal number 1 and the decimal number minus 1, we calculate their binary representations. So the binary representation of 1 is 0 0 1, assuming that we have 3 bits available, and the representation, the binary representation of minus 1, again assuming that we have 3 bits available, is 1 1 1, as we have calculated previously. And the result of this subtraction, or of this addition, better said, so the result of 1 plus minus 1 is 0. And yeah, in this case we can just add up those two binary numbers. So if we calculate 1 plus 1 here on the right hand side, we get 0 and 1 as a carryover. Then we have 0 plus 1 carryover is 0 again, and 1 carryover. Then we have 0 plus 1 carryover is 0 again, and 1 as a carryover, which is an overflow. And again, we can ignore this overflow, and we get as a result 0, which is perfectly correct. However, there are also limits of representable numbers. So most computers have either a 32-bit or a 64-bit architecture. And generally, 32-bit architecture, there you can represent a maximum positive integer of 2 to the power of 32 minus 1. And at the 64-bit system, you have a maximal positive integer of 2 to the power of 64 minus 1. However, Python 3 is very good in handling large numbers. However, the fundamental problem generally persists for computers. So let's look at how Python handles large numbers. As I've already said, Python is great in handling such large numbers. And normally, for those of you who are familiar with other programming languages, like C++ or C, for example, if we have 32-bit integer, like here, we have just a simple integer, which is 32 bits long, defined in binary. You can see here I have 32 ones, and I can print the value out, and also the bit length. So yeah, since the integer is an object, or this is a class, it also has a method called bit length, which returns the number of bits which this number holds. So if we execute this, you see here it first prints out the decimal number of this binary number here, and here at the second line it prints out the number of bits which this number uses, and in this case it needs 32 bits. And now we define a second variable where we add 1 to this number. And normally if we were, for example, using C or C++ as a programming language, we would get a buffer overflow, which means we would add 1 here, and since we have a fixed length of 32 bits, the overflow would be ignored, an exception would be raised, and the value would be 0 again, because if we add 1, all the ones here get to 0, all those ones get 0, and we would get an additional 1 here, and however this will be neglected since it is an overflow, and the value would be then 0 again in the variable. So, but let's look what Python does. If we execute this code cell, you see here that we first print out again the value of this variable. It is still the same large value, and then we print out the value of this variable, which holds the value of the 32-bit integer plus 1, and as you see, it worked perfectly fine. So yeah, it just added 1, as you can see here, and at the end we print out the bit length, and now you see that the new variable has a bit length of 33, which is kind of uncommon, because normally you have either 32 bits or 64 bits integers. And however, Python is really great in handling such large numbers, and has an adaptive bit length. So in the background it performs basically some nice magic, which is capable of handling such cases. So if we print out, for example, using the bin function, we can print out the binary representation of a decimal number. And as you can see here, so the first variable is just has this binary value, which we have defined up here. So yeah, this is correct. And as you can see here, the E33 variable, this is the binary representation here. And as you can see here, we have 1 additional bit here. So basically this is the additional bit. And if we have only 32 bits available, this one, you can see that all the values here are 0, and this one up here is the overflow basically, if we would be using C++, for example, and therefore the value would be 0 in our variable if we add 1 and only have 32 bits available. However, Python is clever. Python knows that we want to add 1 and knows that we need to increase the bit length, and therefore adds 1 additional bit in order to represent our new number. The same also works for 64-bit integers. So here similarly I have defined a 64-bit integer using 64 ones in binary. As you can see here, this number is a binary number because of the prefix 0b. I store it in this variable, then I print it out, and then I also print out the length of the variable again. And you see, this is the value, it's a large number, and it has 64 bits. And again, I build a new variable, i65, which is the previous variable plus 1. Again, I print out the values of both variables, and again, I print out the bit length of the new variable. And as you can see here, again, it perfectly worked. So we added 1, and the new variable has a bit length of 65 bits, which is also very, very uncommon. However, Python is great in handling such large numbers, and yeah, it is capable of doing such calculations. And similarly, I can again print out the binary representation of those two decimal numbers here, and yeah, it's the same as before, just twice so much bits. And if you have ever wondered how large numbers Python can handle, here I have another calculation. Namely, I calculate 9 to the power of 1, 2, 3, 4, 5, so 12,345. I execute this, I print it out, and you see it is quite a large number here. I can scroll a lot. And again, I can print out the length of this variable, the bit length of this variable, or the number of bits which are needed to store this huge number. And yeah, it needs 39,133 bits to store that number in memory, which is quite a lot. And again, I can also print out the binary representation of this decimal number, and you see, yeah, it's quite a lot of zeros and ones. All right. So now let's look at the some conversions. So at this step, we learn how we can convert a binary number into a decimal number. So first we need to write down the binary number, and in this case we have an 8-bit binary number. Then the next step is to write down the position of each bit. The rightmost position is the LSB, so the least significant bit, at position 0. And in this case, since it is an 8-bit number, the leftmost position, also known as the MSB, is the most significant bit, is at position 7 in this case. And then we just write down the base, which is, in case of the binary number, 2 to the power of the position for each position. So we have 2 to the power of 7, starting from the left, and 2 to the power of 6, 2 to the power of 5, and so on, until 2 to the power of 0 for position 0. And then to calculate the decimal number, we just need to sum up all those values and multiplicate it with the binary value. So if we start from the left, we have the binary value 0 times 2 to the power of 7 plus the binary value 0 at position 6, so 0 times 2 to the power of 6 plus then the next position 5, the binary value 1 times 2 to the power of 5, and so on until we hit the last position, which is again binary value 1, so 1 times 2 to the power of 0. And then we sum up all those values, and we just need to calculate those values where the binary value is 1, since all the other values are multiplied with 0. And therefore we have here 32 plus 8 plus 4 plus 2 plus 1, which is 47. So this way we can calculate from binary to decimal. And yeah, here is the formula for the calculation. So to get the decimal number, we just need to build the sum from k 0 to n minus 1, which is the position of x k times 2 to the power of k, where x is the bit value at position k, so xk is the bit value at position k, and n is the number of bits which we have. And in this case we had 8 bits. And yeah, so now we look at the conversion from hexadecimal to decimal. So here we have the hex value 014C, and again we write down the position. So now we start from the right, for example. The rightmost position is position 0, then position 1, position 2, position 3. And then similarly as previously, we write down the base, and since hexadecimal has the base 16, we write 16 to the power of the position. So 16 to the power of 3, 16 to the power of 2, 16 to the power of 1, and 16 to the power of 0. And then, similar as before, we just need to build or to calculate the sum, same as before. So we write, if you start from the left, the value, the hex value, which is 0, so 0 times 16 to the power of 3, plus then the next position, the hex value 1 times 16 to the power of 2, plus 4, so that's the hex value 4 times 16 to the power of 1. And the last step, we have the hex value c, and the value c is equal to a decimal value 12, and therefore we can write 12 times 16 to the power of 0, and then we just need to calculate the sum. So again, we just need to calculate those where we have a value greater than 0 for the hex value, so 260, 256, 64 and 12, build the sum, which is 332. And here on the right hand side you can see a small table for the results of 16 to the power of 0, 16 to the power of 1, and so on, and 16 to the power of 3 is 4096. And again, we can use the same formula as before to get the decimal number. We just need to build the sum from k equals to 0 to n minus 1, and for each sum we need to calculate xk times 16 to the power of k. So similar as before, xk is the hex value at position k, and n is the number of hex digits. And yeah, we have just exchanged the base. Previously we had the base 2, now we had base 16. Alright. So now let's look the other way around. So how can we convert from decimal to binary? So the first step is we divide the number by 2. Then the remainder is the LSB, so the least significant bit, it's the rightmost bit. And then we divide the result again by 2. And the remainder is then the second bit, so the LSB plus 1 bit. And we repeat until the result of the division is 0. So for example, if we have the decimal number 29 and when we want to calculate its binary representation, we divide it by 2, and the remainder of 29 by 2 is 1, so we have 1 remainder. This is then the least significant bit, and then the result is 14, and then we divide 14 by 2 again, and then we have no remainder since we can divide it without the remainder. So 14 divided by 2 is 7 with 0 remainder. and then we again divide the result 7 by 2. 7 divided by 2 is 3 with 1 remainder. And then again we divide 3 by 2, which is 1 with 1 remainder. And then we divide 1 by 2 again, which is not divisible. So we have 1 remainder and the result is 0. So yeah, now we are done since the result of the division is 0. And on the right hand side you can see the result, where the value at the bottom is the MSB, the most significant bit, and the value at the top is the least significant bit. So yeah, you start writing the MSB at the left and the LSB at the right. Now let's look how we can convert from hexadecimal to binary system and vice versa. This is, in my opinion, the easiest conversion. So you can group the binary number in groups of 4 bits. So you can see this, I have inserted the bold black line in the middle in order to separate it into groups of 4 bits. And then you can write again so that the value of each bit at the top. So for example, if we start at the rightmost position, we have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. And then after, so we have now basically write down the values for 4 bits. And then we again start at 0. So we have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So after each 4th bit, we start at position 0 again. And then we can convert those 2 groups of 4 bits into its hexadecimal value. So if we take the right 4 bits, we have 4 ones. And yeah, this is basically the maximum value. So if we have 4 ones, this is equal to the value 15, and the value 15 is F in hexadecimal. And if we look at the next 4 bits at the left hand side, you see this is the binary value 2. This is the decimal value 2, and the decimal value 2 is equal to the hexadecimal value 2. So we can convert each 4 bit into a single hexadecimal number. So here you can see the decimal values and its hexadecimal representations. So you can see yeah, the decimal value 15 and the hexadecimal representation, which is F, and so on. Alright, so you just need to convert 4 bits into decimal, and then just yeah, need to convert basically the decimal to hexadecimal, which is pretty straightforward. So the decimal number 0 is hexadecimal 0, decimal 9 is hexadecimal 9, and then you just need to remember that from 10 on, decimal 10, you start with A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. And that's it. In this sense, I would like to close this lecture with a nice picture which says that there are 10 types of people in the world, those that understand binary and those that don't. And hopefully after this lecture you should understand this quote here. As always, thank you very much for your attention and see you next time.